I will explain the pure diatomic case, which is what like oxygen. And in the later part of the talk, I will motivate the mixed case. So there's some history. So I think it's not clear who studied it first, but the earliest reference that I found was Fowler and Rush book in 1937. In 1960, and simultaneously Michael Fisher and Temperley solved the problem for the square lattice. Then there was some further work, more correlations, asymptotics, phase transitions, etc. Okay, so I don't want to get into a lot of detail, but a lot of work has been done on this model. So let me come to the mathematical formulation. So you have an arbitrary graph G, which I write as V comma E. V is the set of vertices, E is the set of edges. For such a graph, a perfect matching or a dimer covering or a one factor is a subset of edges such that every vertex is incident, sorry, this should be incident, to exactly one edge. So this is what this encapsulates the idea that whenever a diatomic gas sits on the solid, it occupies exactly two of the atoms, and then neither of them are available to be occupied anymore. And so a natural combinatorial question is to find the number, which I'll call mg, of perfect matchings of a graph. So one can generalize this a little bit and give the graph weights on its edges. So for an edge E, A of E is the weight associated to that edge. Then for every dimer configuration, you take the product of the edge weights, which are matched. And when you sum all of them, you get something physicists call the partition function. So that I'll denote by Z sub G. So two simple cases that you can analyze quickly is the complete graph on 2n vertices, K2n. For this graph, the number of perfect matchings is the double factorial of 2n minus 1. And this is easy to see. You can do it recursively. So pick any vertex. It has to be matched with somebody. So you match it with somebody. You can pick that somebody in 2n minus 1 ways. And now you have what remains is a complete graph on 2n minus 2 vertices, and then you repeat. So you will get 2n minus 1 times 2n minus 3, etc. And that's this double factorial is the shorthand for that. Similarly, for the complete bipartite graph, it's easy to see again that it's n factorial. Okay, so I'll maybe not go through this in detail, but these are some simple graphs that you can get an exact formula for. But the original interest was in planar graphs, because the surface of a solid is a plane, and so one was interested in that. And Kasteleyn solved this problem in a beautiful way, and his main idea was to square the model. So instead of considering dimer configurations, he considered pairs of dimer configurations. So, and I've illustrated the idea here. So if your graph is the 5 by 4 square grid, here are two different perfect matchings. And when you superimpose them, one can see without too much difficulty that what you will get are either doubled edges, where in both these copies the same edge was matched, so then you get a doubled edge, or you will get a loop of even length. So these are the only things that can happen. So what Kasteleyn analyzed was a model like this, where there are even loops and doubled edges, and So here there's a slight, I'm lying a little bit. What you actually need to do is to give an orientation to the loop. So that the loop going clockwise and the loop going counterclockwise both contribute. So if that is the case, then one can see that the adjacency matrix of the graph is going to help. So recall that the adjacency matrix of the graph is the matrix indexed by the set of vertices whose, and if V and W are vertices, the VWth entry is 1 if and only if V and W form an edge. And if the graph is undirected, like for us, then A is a symmetric matrix. So now if you take the determinant of this matrix and you use the Leibniz expansion, then you can see that if you decompose, so you consider a term in the determinant indexed by permutation. If you decompose that permutation into cycles, then this is exactly what you get. So you'll get one term for this edge, then one term for this edge, one term for this edge, and so on. And the fact that it forms a cycle corresponds to having a cycle in that permutation. So, a doubled edge corresponds to taking two guys which are transposes of each other. So what this suggests is that the determinant of the adjacency is a natural candidate for the product function. For each cycle, you will get a product of the edge weights, and you multiply them out. What is the problem? The problem is that if you remember, the determinant comes with a sign, and what we want is the sum of all perfect matchings. You don't want a signed sum. You want all terms to contribute with the same sign. So this is the issue. So Kasteleyn also resolved this issue. So first, let me define what an orientation is. The orientation for an undirected graph is just a way of assigning edges to the arrows to the edges. Sorry. So you can assign it any which way you like, and that would be a valid orientation. But for a planar graph, you can define a special orientation, which is now known as the Kasteleyn orientation, in which for every elementary phrase, the number of edges as you go clockwise around the face is odd. So I'll illustrate this with an example in a second. But the key idea is that this is special for a planar graph because we are talking about faces. So recall that a planar graph is a graph that can be embedded in the plane without any crossings. So then you have these elementary faces, and as you go along each face, if you count the number of edges going clockwise, if that is odd, then you get a Kasteleyn orientation. And what Kasteleyn proved is that if you have this Kasteleyn orientation, then the relative sign of two different dimer configurations is 1. So that will guarantee that each dimer configuration comes with the same sign, which is what you want. And he also proved that a Kasteleyn orientation exists for every planar graph. So he essentially proved the following. So if you take the adjacency matrix of the graph and give it a sign, so symmetric, by assigning a sign in the following way. If the orientation is from V to W in the Kasteleyn orientation, then you give it a plus sign. You give the VWth entry a plus sign, otherwise you give it a minus sign. So then you form an antisymmetric matrix. This has to be an even sized matrix because otherwise there cannot be a perfect matching. And then you recall the even antisymmetric matrix. The determinant of an even antisymmetric matrix is a perfect square, and its square root is the Pfaffian. So Kasteleyn proved that the partition function for a planar graph can be calculated using a Pfaffian. So it's a powerful result because it doesn't assume anything other than planarity of the graph. Are there any questions so far? So let me illustrate this with an example, with a really baby example. So consider this square. I have labeled the vertices in this clockwise way, but not all the edge. Oh, sorry, counterclockwise way, and not all of the edges go counterclockwise. I have deliberately chosen the 1,4 edge to go clockwise. All the other edges go anti-clockwise. This is my orientation. So the graph is undirected, but I have given this orientation. Okay, and this is a Kasteleyn orientation because the number of clockwise edges in this placket is 1, which is an odd number. And if you construct the Crystalline matrix, which is using the natural order 1, 2, 3, 4, then I should have said. So I'm giving horizontal edge weights A and vertical edge weights B. So the 1/2th entry is A because the orientation goes from 1 to 2, and the edge is A. And the 2/1th entry is minus A for the same reason. And similarly, the other ones. So if you calculate the Pfaffian of this matrix, you will get A squared plus B squared. And if you think about it a little, you'll see that is the partition function, because there are two possible ways of matching this graph. Either you join 1 to 2 and 3 to 4, that gives you a weight of A squared, or you join 1 to 4 and 2 to 3, that gives you a weight B squared. So this is the illustration of Kasteleyn's theorem in a baby example. So are there any questions about this?
So that's effectively the permanent of the matrix as well, isn't it?
Yeah, so that's right. So I could have taken the permanent of the, or not the permanent, but the Hafnian of the, which is the analog of the permanental analog of the Pfaffian. But that is not so amenable to computation and asymptotics. So that is also even, so that would be, I mean, it's much more, the determinant is, or a Pfaffian is a much nicer object than the permanent or the Hafnian. So yeah, so that's the reason why they were motivated to do it this way.
But this must give some kind of general identity connecting the permanent or the Hafnian and the Pfaffian for these kinds of adjacency matrices of planar graphs or something.
No, because the orientation is this extra data.
Yeah, okay.
And there are many choices of orientations in general, exponentially, even for the Kasteleyn orientation. So I think that one doesn't get something general in that sense. Yeah, shall I go on?
Yep.
Okay, so now I want to tell you a really beautiful theorem. This is also due to Kasteleyn and simultaneously Temperley and Fisher, both in 1961. So you consider the 2m by 2n grid graph. Okay, so this is the graph that one of the examples I showed earlier. You just take a subset 2m rows and 2n columns, and for the moment you don't have to give them any weights. Then what these two groups showed independently is that the number of perfect matchings, sorry, I've written tilings, is given by this amazing product formula. It's 4 to the mn times this product over j going from 1 to m and k going from 1 to n. Sum of two cosine squareds and divide where the arguments are multiples of pi, but where the denominator is an odd number. I mean, it's really an amazing formula because each one of these terms is an irrational number in general. And if you can imagine m and n are large, like, I don't know, 20 and 40, then this will be horribly irrational numbers. And you're summing them, and then you're taking a product over all of these. So a priori, it's not even guaranteed that you're going to get a rational number, let alone an integer, right? And yet the theorem guarantees that this is always an integer, and it's the number of perfect matchings. So just to give you an example, if you take m is n and m is 3 and n is 2, then you get the sum of cosine squared pi by 5, cosine squared pi by 7, etc., etc. And in this case, at least, there are formulas for cosine pi by 5 and cosine pi by 7 and so on. I mean, they're not simple formulas, but they do exist. And this is really a small example. And now you're summing them, so you get these bunch of irrational numbers. And if you multiply all of them out, you get 281, which is exactly that. So it's a really beautiful theorem. And what this, the fact that you get a product formula like that also allows you to do asymptotics. So the quantity important for physicists is called the free energy. Oh, sorry, there's a typo here. This AB should be upstairs. So the free energy, so now instead of, so I should say that there's a formula, there's a variant of this formula where if you give horizontal edges weight A and vertical edges weight B, then you'll get an A squared cos squared and B squared cos squared. So that's the only thing that will change. And it will still be a polynomial in A and B with integer coefficients. So I'm calling that Z sub mn of AB. And if you take the log of the partition function and divide by mn and take the limit m and n go to infinity, of course you want one of m or n to be even, otherwise there's no perfect matching. So that's the slight issue here, but that can be done. And then, so what these guys did is they were able to analyze this. So first of all, using the product formula, you get an integral, and writing it as a Riemann sum integral expression, which involves, so it's a log cosine, and using that, what they did was they took they calculated what's called the density of horizontal dimers. So how many, if you want to know on average how many horizontal dimers there are, then you differentiate this free energy with respect to A and multiply by A. And using some integral identities, they could show that this is exactly given by 1 by pi times tan inverse of A by B. So it has a very compact expression. And now if you integrate this out, you will get a series formula using the famous series expansion of tan inverse. So this is not so tractable as far as I know. But if you take A and B equal to 1, then this is just the alternating sum of the odd reciprocals of the odd integer squares. And this becomes, the free energy becomes g by pi, which is where g is the famous Kasteleyn's constant, which is 1 by 1 squared minus 1 by 3 squared, etc. So it's this alternating sum that I said. And so it's also a fundamental constant. It comes up in asymptotics very often. And one can also calculate the degree of freedom. So if you imagine that how much freedom does each, freedom in some abstract sense, how much freedom does each cell have to get a dimer? That is, since there are mn by 2 dimers, you write it as, if you call this degree of freedom mu, then you write it as mu to the mn by 2, and then mu is exactly e to the 2g over pi. So this gives you an explicit quantity for the degree of freedom for the square lattice. Okay, so this is what I wanted to say about this Dimer model. Are there any questions before I move on?
Yes. Is there a kind of intuitive way to, or interpretation, let's say, of this, like probabilistic interpretation of this G over pi? Like you scale it by
Yeah, well,
R
not
radius, you have the volume of the
sorry,
content of
which one?
a circle.
Sorry, say that again.
So is there a
Sorry, I
kind of
didn't understand.
probabilistic interpretation of this formula, G over pi?
Ah, you mean
You
why
know,
it comes up
pi
here?
is the content of the circle of the
Yes,
disk amount,
yes,
and you know, like you have the full circle, and then you have only a portion of it which is positive in a sense.
right. Yeah. No, there's no. I mean, it's a miracle
Yeah.
that these two constants show up. I mean, I don't know any other interpretation of
Okay.
this. Yeah. So yeah, and yeah, that's another nice thing about this whole work. Um, yeah, right. So I don't know any probabilistic interpretation. In general, the free energy need not be less than one. I should say that. So one doesn't expect a probabilistic interpretation. But this quantity mu you can think of as entropy, is some kind of entropy. Yeah. Shall I go on? Michael, can I go on?
Yes, sure, go on.
Okay. So now I want to describe a generalization of this. So this is what I call the monopole dimer model. So again, G is a simple planar graph, undirected. But now I need both vertex weights and edge weights. So to each vertex V, I'll give the weight x sub V. And edge weights, if V and VV prime is an edge, then I give the weight A sub VV prime. And that's the same as V prime V. And now, instead of, so my configurations for the dimer model earlier were just pairs of edges, disjoint, and non-adjacent. But here I'll have something more complicated. So I either have isolated vertices, which I'll call monopoles. I have oriented loops of even length, or I have doubled edges. So these last two are exactly the same as the dimer model. And the reason for calling these monopoles is something I'll explain in a second. So this has to do with the notion of Deluxe Strings. So Dirac had this beautiful idea that if there is a single magnetic monopole in the universe, that would explain why charge is quantized. Um, uh, like why we have charges in multiples of the fundamental constant. So here's an example. So again, my graph is this 5x4 grid graph, and here's a configuration. So these two vertices don't talk to anybody, so they're just isolated. These are red ones are loops of even length, and blue ones are double edges as before. Okay, so again, you should think of these loops as having an orientation, so either clockwise or counterclockwise. So why is this a generalization? So you can decompose, just like for the dimer model, you can decompose such a configuration into a bunch of monomer dimer configurations. So where I will have dimer adjacent to anybody else. So if you take two of these guys where the monopoles are at the same location and you superimpose them, you're going to get configurations like over here. And so in particular, if there were no monopoles, then you would exactly get the dimer model. So now I have to tell you how to give weights, and this explains the terminology. So the weight of a monopole at a vertex V is just x sub V, the weight of the vertex weight. For a loop, this is where things differ from Kasteleyn's model. So you take, if a loop is of length 2n is like so, v1 up to v2n followed by v1, then you take the edge weights of the successive vertices along the loop. The only new complication is you give a sign. You give a sign proportion raised of -1 raised to the number of monopoles enclosed by the loop. So this is why that I use the term monopole instead of a monomer, because this is some akin to what Dirac, the computation that Dirac does carrying currents, then this is very, very much analogous to Dirac's computation. So that's why I call these monopoles. And the weight of a monopole dimer configuration is just the product of the loop weights and the monopole weight. Of course, the sum over weights of configurations. So again, in the same example, if I give horizontal edges weight A, vertical edges weight B, and vertices weight X, then I get an X squared for these two monopoles. I get A to the 10, B to the 8. I get a minus sign because this loop encloses the one monopole. This loop does not. So there's exactly one minus sign. So that is what comes up here. So from a physics point of view, I should admit that these are less interesting because there are signs, but there is still something nice going on. So I'll explain that in a second. So I just recall again what the Kasteleyn orientation is. So the number of clockwise edges in every face is odd. Again, this is for planar graph, and this was Kasteleyn's theorem. So the main result is the following. So I define the modified Kasteleyn matrix, which is exactly as before. So you have a Kasteleyn orientation, you make the matrix of diagonal entries skew symmetric exactly as before, but you also add diagonal entries corresponding to the vertex weights. So here you need both vertex weights and edge weights. If so on the diagonal. And so this is the theorem. So if K is this modified Kasteleyn matrix for a planar graph, then the partition function for the monopole dimer model is exactly the determinant of this K. So now notice that this is no longer a skew symmetric matrix because your diagonal entries are not necessarily zero. So one doesn't in principle a priori expect something nice. So just to go over the same example, this is the same Kasteleyn orientation. So I just added x's on the diagonal. So in other words, I just added a multiple of the identity matrix to the old Kasteleyn matrix. And now if you take the determinant, you will get these things. So I've just separated it out according to the powers of x. So x to the 4 corresponds to the fact that all 4 are monopoles. X squared corresponds to the fact that 2 of them are monopoles. So you cannot have monopoles just at 1 and 3 because 2 and 4, what will they do? So if 1 and 2 form monopoles, then there's a doubled edge at 3, 4. So that will give you an A squared. Similarly, if 3 and 4 are monopoles, 1, 2 will be a doubled edge and that will give you another A squared. So you'll get a 2A squared x squared from here. Similarly, you'll get 2B squared x squared for these two. And then the remaining is just without monopoles. So A to the 4 is this doubled edge and this doubled edge, B to the 4 is the other one, and 2A squared B squared corresponds to this loop, one going clockwise, one going anticlockwise. So this explains all the terms. And the proof idea is kind of following the nose of Kasteleyn's proof. So maybe since I'm low on time, I don't want to get into all the details. And as I said before, if all the vertex weights are 0, then this becomes K becomes manifestly even antisymmetric. even skew symmetric, and therefore it becomes the square of the Pfaffian, and this then makes perfect sense because we've essentially squared the diamond model. So now let me on subsets of Z2. So again, if this now I take the m by n rectangular grid, now I don't need to assume that m and n are even anymore. I define this complicated looking function, which, okay, it just also involves the cosine squareds. Then the theorem is that if you take the, so I should have said, I again take horizontal edge weights A, vertical edge weights B, and vertex weights X, and I take my original Kasteleyn orientation. So the partition function of the monopole diamond model is very much analogous to the formulas of Kasteleyn, or the formula of Kasteleyn and Fisher-Temperley, except that there's an x squared added to these terms. And you have to, there's a change of indices and so on. But this thing is a squared times there's a bunch of factors if one of them, if at least one of them is odd. Okay? So the thing, again, as I keep stressing again and again, this is not obvious that it's a polynomial with integer coefficients at all. But this comes up in the proof. So, yeah, so, right. So the key idea is not much. I mean, the point is that the modified Kasteleyn matrix in this case is just a multiple of the identity matrix added to the original Kasteleyn matrix. So their method, which was an explicit diagonalization, works automatically. And all you have to do is just analyze things a little carefully. So, I want you to notice one thing is that if m and n are even, this becomes a perfect square. The partition function becomes a perfect square.
Arvind, what is YMBX and YNBX?
That is just this complicated thing over here.
Oh, okay. Sorry, I missed it.
Okay. Yeah. Sorry, I went through it a little fast. It's some non-trivial function, and this y is not necessarily a nice function in general. I mean, doesn't have integer coefficients as a polynomial in B and X. But when you multiply everything out, it's all nice. So, right.
So is this
Yeah, go ahead.
partition function is just the characteristic polynomial of the Kasteleyn matrix with variable minus x?
Exactly. Yes. That's all. That's all there is. Yes.
Yeah. So then the eigenvalues that Kasteleyn and Fisher and Temperley calculated, you just use those.
Yeah. So with this choice of Kasteleyn orientation, the eigenvalues are not so nice. But what happens is they break it up into 2 by 2 blocks, and that's why you have this x squared business. So you're taking a product of determinants or characteristic polynomials of 2 by 2 matrices essentially after some transformation. Right. So exactly. So the proof is essentially their proof. I mean, there's nothing to do. So the main idea was to formulate the interesting thing was the formulation. The difficult part was the formulation of the model. Yeah. And there's some special cases when they're odd and so on. So I don't want to get into that. So the 2 by 2 example that I showed you and I went through in detail, like here. So if you if you like to factor things, then you would have noticed that this is actually x squared plus a squared plus b squared. So it's not this is not obvious a priori, and this is not some general theorem in linear algebra because the matrices are no longer skew symmetric because of this diagonal non-zero entries. But yet you get a square. So there's something nice going on. Okay, so maybe let me not get into this because I mean you guys are special functions people, I should I should at least spend some time on special functions. So the remaining, what I want to do is to give you a flavor of the asymptotic analysis that goes here. So before that, I want to recall quickly what elliptic integral is. An integral like this, and these are classical objects. And if you take this parameter phi to be pi by 2, then you get the complete elliptic integral denoted k of m. Now, by the way, this m is literally called the parameter in this terminology, and it's taken to be between 0 and 1. And similarly, the incomplete elliptic integral of the second kind is similar to the first one, except that the integrand, this function is in the numerator instead of the denominator. And again, if you take the limit, the upper limit to be pi by 2, you get the complete elliptic integral. Okay. Two more. And that's it. The Jacobi zeta function is some function involving these four guys, the four functions I defined in the previous slide. And the Heumann lambda function is some even more complicated object involving these guys. It involves both the 1 minus m, which is the complementary parameter, and m. So, and in particular, this Heumann lambda function has come up in other problems in various physical contexts, vibrations of non-Hookean strings and inductances of cylindrical solenoids. So cylinders seem to like this function for some reason. So this is an elliptic integral of the third kind. So this was the background, and now I go through the same free energy computation that I went through earlier. I take log of the partition function, which now depends on a, b, and x. So remember, I'm doing the rectangular grid, m by n grid. A is the weight of the horizontal edge, b is the weight of the vertical edge, and x is the vertex weight. So analogous to what Fisher and Kasteleyn did, you have this product formula, you take the log, it becomes a sum, you write it as a Riemann sum, and then you get an integral formulation which involves log and cosine squareds. So it's not exactly doable as far as I know. And again, you can calculate the density of the dimers. So how likely is it that you're going to find an A-type or a B-type dimer? By the way, I should say that probabilistic interpretations are not legal anymore, because things have signs. So you cannot interpret things probabilistically, at least in an obvious way. But okay. So things are symmetric between A and B. So let's look at the row of A. So you differentiate it under the integral sign, and you can integrate one variable out, and then you get an integral like this, where this parameter y is the square root of x squared plus 4b squared. And this turns out to be exactly 1 minus this Heumann lambda function with these parameters, theta sub a and this parameter. So theta sub a is given by tan inverse of this complicated thing, and m is also given in terms of a, b, and x. So, and it's exactly 1 minus that quantity. So I was really surprised when this came up, and it was not obvious. I had to go through some books of tables of elliptic integral. Formulas involving elliptic integrals and things like that. Abramovich and Stegun and things like that. So, it took me some work to get this formula, just digging. But I was really surprised that it's 1 minus, just 1 minus a known function and no other parameters. So, and using some other formulas involving the Heumann lambda function, you can write this density of monopoles, quite simply, which involves just the complete elliptic integral of the first kind with some parameters, with some prefactors. Sorry. And now, if I use this, one of the series expansions for the complete elliptic integral, I get a formula like this. So it's an infinite sum involving, so these are the double factorials which came up earlier, and this is these parameters. And now if you integrate this term by term, assuming a is greater than b, I need that because I take powers of a squared minus b squared. Then this is an infinite sum of two f1s. And with some other complicated things. So I would like to know if from you guys if one can hope for an analytic, or not an analytic, but at least an some expression involving special functions of this free energy, and that would be really nice. As of now, I don't have anything. This is the best I have, but it's clearly not very nice. The problem is also that this parameter is arbitrary. I mean, there's no restriction on the parameter. But these guys, well, this also depend on J, so I don't know. It's at least the usual software packages couldn't do anything, and I couldn't find any such thing in the literature either. But in the case A and B are 1, this becomes quite nice. So it's some log, there's a log term, and then this becomes a 4f3. And in particular, with simple parameters. And in particular, if I set x equal to 0, then I get 2g over pi, which is exactly this. So this is the square of the Dimer model. So you get this factor of 2 extra. So it all matches very well, very nicely. So I was rather pleased about that. So yeah, so I think I'm running out of time, right, Gaurav? How much time do I have? Gaurav or Krishnan, are you around?
Yeah. So yeah, you can up to you. You can open for questions or.
Yeah, maybe I'll just say what I did in the last section, and then I'll not go through details because it's complicated. So as I said, Z2M2N, for the monopole Dimer model, is a perfect square in a polynomial, and similarly, if I take this cycle graph, which is also a planar graph, which is just n vertices arranged in the form of a circle, if I take n congruent to 0 mod 4, then again the partition function becomes a perfect square. So I started to look at or try to understand when this is a perfect square, and can I give a combinatorial interpretation of the square root, just like analogous to the Pfaffian. And maybe without going through too much detail, I can just say, let me just explain with an example. So if I take if I take the monopole Dimer model on a graph like this, where there is a symmetry, there's an involution without fixed points that preserves the graph. So in this case, if I rotate the whole picture by 180 degrees, the graph is invariant, including the labelings, both the vertex weights, and edge weights. So as you can see, there's a beta here, alpha here, d here, b here, etc. In such cases, the partition function is a perfect square, and for the square root, I define another graph-like object which I call a dicot, which is like a graph with two kinds of edges. So the solid and dashed edges, and I define a monopole Dimer like model on these guys, and these are exactly what are needed. These are the square roots of the monopole Dimer model. So So what you do is you quotient out by the symmetry and you add some extra dashed edges, and you can define a model on that which has the right properties. And yeah, that works. Okay, so I think I'm out of time, so I should stop now. So thank you for your attention. So yeah, so are there any questions?
Any questions?
Should I stop sharing?
Am I audible to you?
Yes. I can't see
Yes,
you
sir.
though.
Actually, the camera is not working fine, so
Okay.
I can't on it.
Okay.
And I'm Anita Arora. So I have a question on last page you have introduced a die code.
Yeah, but I didn't define
Right.
it very well. So let's. I mean, yeah. So maybe it's not.
No, I'm not talking about die code, but just as in the Pfaffian, the original graph should be on even number of vertices. So for die code also, the original graph should be on even number of vertices.
No, not necessary. Even as I said, the monopole diamond model, M and N could be odd, right? So here, these are various cases. So the monopole diamond model does not require even number of edges because you can have any number of monopoles. They are all isolated. So there's no restriction like that. Yeah.
Thank you.
Yeah. Should I stop sharing or Gaurav?
Let's just wait for some more questions. I mean,
Okay.
then one can stop.
So were you the first person to consider this monopole diamond model?
Yeah, as far as I know, yes. I asked when I came up with this. I asked many
That's
other
right,
people,
exactly.
It seemed to
Yeah,
be such a natural thing that I thought this has to be done. But I think one of the reasons this was not done, I could be wrong, but my sense was that the fact that there are signs makes it less interesting to at least the physicists, so they were less interested. But I haven't shown the figures, the plots here, but actually I can prove that this partition function is always positive. So even though some terms are negative, they are in the minority.
Mm-hmm.
And I can also prove that probabilities, I mean the things which are proxies for probabilities, they are also positive. So and this is my personal opinion, that one should think of the square root of this monopole diamond model as really a monomer diamond model.
Yeah.
So there are some other hints, like for example, there are no phase transitions in this model, just like there are no phase transitions in the monodiamond model. So yeah, so I have some vague intuition that that is the case, but proving any of this is difficult. Yeah.
Okay, any more questions? Okay, so let's thank the speaker, and please be sure to unmute yourself before clapping. So, I don't know if anybody is thanking.
Thank you.
Thank you.
Arvind, I hope you're okay.
Yeah, I was telling them before you joined, I reached Bangalore on Monday. I managed to get by just in the nick of time.
And you're home quarantine now, huh? So you
Yeah,
can give
home
lots of
quarantine, 2 weeks.
seminars, huh? You can give
Sorry?
lots of seminars,
Yeah, I know. Yeah. I mean, but it's a bit hard, as you saw. I mean, there's lots of distraction.
Okay, so then
Okay.
we're done.
Do share the slides. Sorry, Arvind, if you can share the slides with Gaurav,
Sure.
or
I'll send you the slides right away. Yeah.
I would say the talk was quite fast. We want to catch up the details.
Okay. Oh, yeah, you should have interrupted
No,
me.
not at all. We will read them at our leisure. Thanks.
nice
Thanks a lot.
idea. Thank you.
Yes, nice talk. Thank you.
Yeah,
Thank you very much for everybody coming in. And we'll see you in another couple of weeks, I suppose.
Thanks for coming.
Okay.
Okay.
So I'm going to, I guess, stop it.
Bye bye.